Okay, let's get started, guys.
Does anybody know for this what H-naught 3s is? It's the ideal isotopic. So what is it? Oh, so H-naught 3 is just. Then why don't we use H-naught 2s?
Because H02 is the same starting condition based on how we define it.
Oh, okay, so H-naught 3 is the change. And then why do we use ideal over actual?
You have to draw this TS diagram.
Guys, let me have your attention. Let's get back to some of the basics so that you understand the more advanced topics a little bit. So some of these I had covered on the slides earlier, but I thought let me walk you through even the intermediate steps, some of which I had skipped. Coming to the particular point that you're looking here, we are looking at the planar motion, both in Cartesian coordinates and the polar coordinates. It's not a whole big deal getting to 3D for this because both of them bring in a z coordinate which is coming out of the plane of the board with a unit vector k hat. So adding that is not a big deal because k hat, like I hat and j hat, are constants, and therefore there's no time derivative associated with them, and therefore it's just a z dot times z dot times k hat for the velocity and z double dot times k hat for the acceleration that you have to add if you want to move from 2D to 3D, which is not a big deal, right? So let's come back, and also in terms of extending this to the other way of looking at 3D is spherical coordinates. Again, there is a little bit of complication there, but once you understand how to deal with theta, the same logic works as far as dealing with phi, which is the polar angle. So we call this as the radial coordinate. And this as the azimuthal coordinate. And it's the equivalent way of the same position given in terms of x and y as well as r and theta. And this position vector we will call by the name small p. It's a vector as the name itself suggests. Yeah, Andrew.
What was it we used not for the radial coordinate, for the other one?
Azimuthal, A-Z-I-M-U-T-H-A-L. Yeah. Okay, so if you had the spherical coordinate, the third one would be a phi, that would be called a polar angle. Though this is the polar coordinate system, the name is such. Okay. Coming to the position vector p, now the same position vector can be expressed either in terms of x, y, I, k, I, j system, or the r theta, er hat and e theta hat system. Okay, so we will try to do both, and then we will try to understand what it is. So you very clearly know that when you say the coordinate is x, y, obviously it means that it's a distance x on the x axis and a distance y on the y-axis. Okay, I think I'm spoiled using the iPad, so after drawing the line, I'm waiting for a while to let it become straight. It wasn't. Okay, now, so very clearly you see that one of the points is 0, 0, the other is x, y, and x is along the I hat direction, y is along the j hat direction. So very clearly you are aware that this is nothing but x times I hat plus y times j hat. Okay, whereas in the case of the polar coordinate, it's even simpler. As we already saw, the position vector is just r times er hat, because er hat is defined as a unit vector over here, right? So this is your er hat, and it's a distance r which is being traversed in that particular direction. So the same thing p now can also be written as r times er hat, right? Now we can correlate these things quite easily, because we know that we are introducing that azimuthal angle here, theta, which is how the point P got its coordinates r comma theta, and we take it as clockwise, counterclockwise, going from the x-axis, 0 at the being 0 at the x-axis, and then 90 at the y-axis, and so on and so forth, right? So now this is the simple geometry which you are very aware from a high schooler or even middle school itself, right? Now the question is, we would like to every now and then shift from one coordinate system to another, so we need to have transformations for that. And now that we know this is x and this is y, the height is y, and this is r, very easily you can see, using trigonometric relations of sine theta, cosine theta, and tan theta, you can arrive at 3 equations. Okay. Now just to keep things a little decluttered on the whiteboard here, I will define these short forms. By c theta, c subscript theta, I mean cosine of theta, which in turn is a function of time, just like r, x, and y, all of them are functions of t in general, the time, right? So similarly, I will abbreviate sine theta as s theta, and tan theta as t theta. Okay. So now from that, it's very clear that if you're looking at cosine theta, it's the adjacent side. If just take this triangle over here, let me just call it Q. So taking the triangle OPQ at the angle subtended at O is theta, and therefore you see that cosine theta is nothing but the adjacent side divided by the hypotenuse, in this case is r, right? So that is one equation we have. Similarly, sine theta is the opposite side, which, because this is y, this is also y, and therefore it is y divided by r, right? And tan theta is the ratio of these two, or you can think of it as opposite by adjacent, which is y by x. Okay. Now we have a way of writing from one system to another. We want to get x and y in terms of r and theta. All you have to do is to take r to the left hand side in the first two equations. So then you see that you have this set of equations that x is equal to r cosine theta, y is equal to r sine theta. So this is a transformation from the r theta system to the xy system. And similarly, we want the other way around. Already we have one expression over there. From this we can get to theta, which is equal to tan inverse of y by x. And here's where we introduce the concept of arctan 2 because we need to test for this sign of y and x. Okay, you see this y by x can be positive in two quadrants. Okay, if you look at the quadrant, if you just try to extend this, I will draw it separately over here to avoid clutter there. So this is x and this is y. You know that in a system like this you have, I don't know if you are familiar with this mnemonic we used to use in schools in India. All students take coffee. So we say A, S, T, C to refer to the fact that all three angles, cosine, sine and tan, are positive there. Only sine is positive, only tan is positive, only cos is positive over there, right? Of course, that you can also check from the actual angles. You can see that indeed is true. Okay. Now, keeping that in mind, and also the fact that both x and y are positive here, and both x and y are negative here. That's the third quadrant. This is the first quadrant, second, third, and fourth quadrant. So you see, both first and third quadrant have y by x positive. One because y by x both are positive, the other because both are negative, and therefore in both these coordinates, both these quadrants, you will have y by x the same value, same positive value. Similarly, on the other hand, if you look at the second and the fourth quadrant, either one of them, like in the second quadrant, y is positive but x is negative. In the fourth quadrant, it's the other way around. Okay, x is positive and y is negative. So therefore, in both those quadrants, second and fourth, the even quadrants, you will have y by x, the ratio being negative, and therefore there can be an ambiguity about theta, whether if it is in the first quadrant, it might as well be in the third quadrant. If it's in the second quadrant, it might as well be in the fourth quadrant. So which is where Fortran in 1961, that's formula translation, a software language, software which is used a lot by engineers, some even today. That is essentially taking a new definition for the inverse tan, which they defined as arctan 2, wherein they check for the sign of one of these quantities, in particular x. Okay, so if you check where x is positive, then obviously you can distinguish between first and third quadrant, similarly between second and fourth quadrant as well. Okay, so in that case, that ambiguity of theta, the possibility of it having two values is removed, and therefore you are okay with it. So that's the first way you transform from the xy system to the r theta system. The other, obviously, you need r, for which we can just square these two and add them up. So these two equations, if I add up x squared plus y squared, I get as r squared cosine squared plus r squared sine squared. I can take out r squared common, it becomes cosine squared theta plus sine squared theta, which is 1, as you know, and therefore x squared plus y squared is equal to r squared, and therefore r can be written as the square root of x squared plus y squared. Once again, just like theta, you had the issue of dual values and you had to choose one of them. R also you have dual values because the square root is also a function where you can have plus or minus, but you know that from the physical argument, r has to always be positive, and therefore you will have this as the positive square root, which we will explicitly mention here as positive over here, right? Now, this is the second set. So these two boxed equations together help you to transform from one coordinate system to another. But now remember that we are not just dealing with scalars, we are dealing with vectors. And all those vectors are going to be expressed in terms of unit vectors which are associated with each of these systems. With the xy system, you have I hat and j hat. Like already mentioned, all the hatted quantities have a magnitude 1 and they remain 1 throughout. Okay. Of course, I and j, even the direction remains the same, but er hat and e theta hat, only the magnitude remains the same, the direction changes. So theta, e theta is defined as perpendicular to er hat, once again giving rise to er hat cross e theta hat, a positive k hat. So that is the direction in which you are moving, the anti-clockwise direction is positive for this. So this is your e theta hat. Okay, so you have er hat and e theta hat. It's not enough for me to get just r and theta in terms of x and y. I also want to get my e theta and er hats with respect to I hat and j hat, which is what we will do next. Okay, so now let's take this portion over here and blow it up. So all of these are unit vectors, and therefore if I draw a circle of unit radius, very clearly the arrow heads should all fall on that particular circle. Okay, the unit circle. So now it's quite easy to go to the same kind of trigonometry triangles that we already encountered over there. So all that you have to do to get to ER hat, for example, is just to go add two vectors, one vector here and the other vector over there, right? Now this vector over here, we know if it goes all the way up to the unit circle, then it is I hat. But if it doesn't, it's only up to here, then we know the magnitude of the hypotenuse is 1. Once again, because of the angle that you have and these being parallel lines to these two, you will have this also as theta. So now you see this is magnitude of the hypotenuse is 1 because it's a unit vector, ER hat. And this is adjacent side, so it just becomes 1 times cos theta, right? So which is cosine theta, which is what should give you the first component of your ER hat is 1 times cosine theta, right, along the I hat direction, okay? But that's not all, right? So to get from this point O to this point P, let's say, it's not the same O and P there I'm talking about, we're just talking of two different points here on the unit circle at this particular location. So we are looking at going from this location to here. We are trying to go, instead of directly along that, by a horizontal trip and a vertical trip, right? So now the horizontal trip is what I have already accounted for. The hypotenuse times the adjacent cosine theta gives you the adjacent side, but that's parallel to the I hat direction. So I have that. Now I have to go in the vertical direction. Obviously that is parallel to J hat. How much is it? That is the opposite side for this triangle, for the angle theta, and that opposite side times the hypotenuse, divided by the hypotenuse, which is 1, would be sine theta, and therefore 1 times sine theta is what I need to add to that. Okay, so from this very clearly we have derived ER hat in terms of I and J, okay, which is one of the important things that we will need later on. Okay, so similarly, if you get E theta, you can calculate E theta as well. You can do it as a homework. You can, not to show over here, but just for your own satisfaction. Turns out to be this. Okay, so now you have ER hat and E theta hat purely from trigonometry and vector addition, because you know that to go from one point to another point, you can go through any other intermediate point and get there. Just like that, we have gone through this particular thing, root, in order to get to P, in order to calculate your ER hat. Similarly, your E theta hat can be calculated as going a distance this way and a distance this way. So essentially these two vectors are getting added up. This vector is what you see is in the negative I hat direction, which is what I have put here, and which is, and of course the theta angle is now different, because of which you have that theta which is over here, right? Because to this is perpendicular, and to this is perpendicular, and therefore you have the sine theta is the magnitude you're going along the x direction, but in the negative x axis, and therefore you have a minus I hat which is multiplying sine theta, similarly a positive cosine theta which is multiplying your E theta hat, and therefore you are having both ER hat and E theta hat over here. Now the reason why this is important is, now we want to get to the velocity and acceleration in the polar coordinate system, and there you know that it's not only r and theta which are going to vary with respect to time. R and theta, just like x and y, are functions of time. R and theta are functions of time, so are the unit vectors ER hat and E theta hat. Why? Because even though I hat and J hat are constants, it is depending on cosine theta and sine theta, and theta in turn is depending on time. It is a function of time, and therefore through theta, er and e hat are functions of time. So if I want to get er hat dot, for example, I have to take er hat comma theta and then multiply it with theta dot, then I will get er hat dot, okay, which is what we can very easily do. So if you can see that the first equation there, I can use to get er hat dot. So there's no product or nothing, just the only one term in each one of them, but there's a chain rule because I want the derivative with respect to time, and this is a unit vector, and therefore I have to specify in which frame I am taking this particular derivative. I will take that in the same I frame in which your I and j are fixed. So when we do that, I have to specify that this derivative is being taken in the I frame, right? So when you do that, you can see that it is, I have to just take the derivative with respect to theta. Cosine theta becomes minus sine theta, and then I have to take the derivative of theta, which is with time, which is theta dot, and then of course I hat remains as it is. Why I hat remains as it is because I have specified I as a pre-superscript here. If I had taken with respect to any other frame in general, I dot would also have been there. That's another term that would have to be accounted for, which is why specifying this pre-superscript uppercase I is so very important. Then let's go to the second term over there, that is sine theta. So that becomes cosine theta times theta dot, and that's going to be multiplying your j hat. Okay. Now you see theta dot is common for both of these, so we can take that out, and we see what is inside is just minus s theta I hat plus c theta j hat. Okay. Now you see, you go back to this, you see that is exactly what is there within the bracket there is nothing but your e theta hat. Okay. So I can just substitute for this bracketed term from here and get e theta hat. So that is just theta dot times e theta hat. Okay. So this is one equation we already have in place, that er dot we have found out. Similarly, we need to get e theta dot as well. It's a straightforward, similar approach. So the expression for e theta is here, which will give you minus s theta theta dot I hat plus the cosine theta will also become negative. Oops, what did I do? Oh, this should be cosine theta. Okay, so the first term here is minus s theta I hat. So when I take the derivative, it becomes cosine theta and then theta dot. Okay, then I go to the second term over here. The derivative of cosine theta is negative sine theta. I multiply that with theta dot because I am taking derivative with respect to time rather than theta. And then I have the unit vector j hat. Okay, so now that I have this, I can once again take theta dot common out of this, and I also minus sine is common for both. So I have c theta I hat plus s theta j hat, which is nothing but your er hat. So once you recognize that, you write this as minus theta dot er hat. Are these derivations clear to all of you? Any doubts, questions? Clear? Okay, good. So let's just write that out on one corner because we'll need those later on. Okay. So now that we have this, we know that we are not happy enough with the velocities alone. We need the accelerations as well, which means we will have second derivatives of ER and E theta with respect to time, which is what we will do next. We want to take the second derivative of those quantities. Okay. So let's start with the first one, ER hat, the radial unit vector. We want to take the second derivative of that, right? Again, I have to specify the frame with respect to which I am taking. Because I am taking it as I can treat I hat and j hat, the small I hat and small j hat as constant, makes things simple for us, okay? Now, coming to that, we have a product of two quantities. So I can use the product rule. I take the time derivative of this and keep that as it is, and vice versa. So I would have theta double dot times E theta hat. Okay. Then the second term would be theta dot as it is, and taking the dot of the second term, which is E theta hat dot. Now I can substitute for, and all of these, of course, these dots, whenever I take, it has to be with respect to I. Okay. So you see that I didn't need to specify I here because there is no derivative here. Okay. Whereas once there is a derivative, I need to specify with respect to which frame I'm taking that derivative. Now, this E theta I dot we already have here as an expression. So I can write that as minus theta dot ER hat, right? So now that we have that, we see that there's a positive sign, negative sign, therefore this becomes negative. And then there's a theta dot there as well as here, so it becomes theta dot squared. And then you have ER hat, okay? So let's rewrite this, theta double dot E theta hat minus theta dot squared along ER hat. Okay, so now we have ER double dot. Similarly, we want E theta double dot also, because that's also going to be part of our acceleration expressions. Once again, taken time derivatives, both the time derivatives are taken with respect to the inertial frame of reference. So I have to start with E theta dot, take the already first derivative is with respect to time is taken. I need to take the second time derivative of this expression. So once again, it's product rule, because it's product of two things, both of which are dependent on theta and on time as well. So which means that I will take that minus theta dot will become minus theta double dot, and ER hat will remain as it is. And the second term will be minus theta dot times ER hat dot, whose expression we already have over here, the first equation there, which we substitute as theta dot times E theta hat. Right? Once again, we have a theta dot squared in the second term, like in the first equation. Let's rewrite that. The first term as it is, theta double dot along ER hat, and a minus theta dot squared along your E theta. Okay, so you see that as you take more and more time derivatives, things get more and more complicated. Yes, Andrew?
So I understand for the position vector, the E like sub r, but lower, it was from before that we were talking
Okay.
It's like the third box.
Oh yeah, here,
Yes.
yeah. Okay, okay.
I understand the cosine theta I, sine theta j. Can you re-explain the sine, negative sine theta I?
This one?
Yeah.
Yeah, okay. So your E theta hat is what we want to get, right? So let's blow up this particular region, right? This is your E theta hat. Okay. So now you have, let's say we draw once again a unit circle, which means all vectors from the center there are going to be of unit magnitude, right? Now we have a unit vector there, which is your j hat. Okay. Whereas this is your minus I hat, right? Because it's the negative x-axis, right? Now we want to get to E theta, which is what we want an expression for in terms of I hat and j hat. So this one vector, I can write it as the sum of two vectors, one going along this and the other going along this. Okay. So the one which is going along I hat is along the negative direction, and that is multiplied by sine theta, because this is theta now. Okay. So no longer this is theta, this is theta. So sine theta is opposite side. Okay. So you're getting sine theta as the magnitude, but it's in the negative I hat direction, and therefore it's multiplying minus I hat. Similarly, this becomes the adjacent side for that angle theta. So therefore it's cosine theta is the magnitude, because the hypotenuse is 1, because it's a unit circle, right? Therefore the hypotenuse is always 1, which is why, in fact, the whole thing, if you take even along I and j, it's going to be 1. And then you see, therefore, the first term is this vector, the second term here is this vector. So this vector plus this vector gives you the vector that we are interested in, E theta. Okay. Okay, any other questions or doubts in the second derivative?
There is
Okay.
some physical significance, it looks like. The differential of ER is theta E theta. It's a tangent again.
Yeah,
Whereas
yeah.
differential of this is a tangent to that.
Yeah.
So both of them are tangent to each other.
Very good. Yeah, good point there. See, and this is something that is not peculiar to ER and E theta. Any vector of constant magnitude, if you take its derivative, then it will always be in the plane which is perpendicular to that vector. Why? Because you see, its magnitude can't change. It's a constant vector. Amplitude is constant. So if at all it changes, which is why it has a derivative, it can only change in a tangential direction, which means that if you take an infinitesimal portion around that, it forms this plane which is perpendicular to that.
It's always perpendicular.
And the quantities that we are taking the derivative of here, ER hat, E theta hat, they're all constant vectors, because by definition they are unit vectors. Their magnitude is always 1, right? So magnitude of ER hat, magnitude of E theta hat, I hat, j hat, all of these are 1, right? So it's constant, right? And it need not be 1, it need not be a unit vector. Any constant vector for that matter, very clearly by definition, if you say it's constant, the only way it can change is tangential to itself. And if you take a small portion which is tangential in all directions, it essentially becomes a plane. So it becomes a plane which is perpendicular to that. So a good point that you brought out, yeah.
So that means
Yeah.
the curly is also answered. That is the reason why you take cross product. It is always in the other
Exactly,
direction that
exactly,
it goes
yeah, yeah.
when you go into the third
Correct,
dimension.
correct. It's corollary. Yeah. Good. Any questions? Okay, good. So now that we have the second derivatives also in place, let's just box that and keep it aside. So these are the two equations we will need when we evaluate the accelerations, whereas yeah, this one is what we will need when we want to evaluate the velocities in the polar coordinate. And as I said, going from this to cylindrical is very straightforward, adding a z dot times k hat to the velocity and z double dot times k hat to the acceleration. So whatever, even though just to explain clearly on the board, I've taken a 2D problem, polar coordinates, the same thing, exact same thing is valid for the cylindrical coordinates as well. Okay. And in fact, the perpendicular plane that we are talking about will involve in the 3 dimension the z coordinate also, but it does not change in that direction, so that doesn't contribute. Okay. So now that we have these dots and double dots for the unit vectors, let's go back to the position vector and now see how we can get to the velocity and the acceleration. Because remember, all that we are interested in is the position vector r. We are interested in the position vector's first time derivative in the inertial frame, which is your velocity vector in the inertial frame, and your acceleration in the inertial frame is going to be given by r double dot, right? Now to calculate r dot and r double dot, we need an expression for r, which we have already written. This is the magnitude of that vector is r. Okay, we are using the same symbol, r without of course the underline or over bar, and that refers to the magnitude of the vector r, and then it's along the radial direction, which is having a unit vector er hat. That's why, as we said, this is so much simpler compared to the Cartesian coordinate frame, where we had to put x I hat plus y j hat, okay, even in the 2D problem. Now, instead of 2 terms, we have 1 term, but the complication sets in once we get to the time derivatives, because of the fact that not only r, unlike in Cartesian coordinate system where only x and y are needed to be taken the derivatives of, here we have to take the time derivative of er hat as well, but luckily we have already done that and put it aside over here, right? So we can take advantage of that. So once we do that, we have this is a product, so once again the product rule is to be used over here. So I have to take first r dot, and which is the magnitude, remember, not the vector, r dot times er hat as it is. The second term will be r as it is, but now multiplying er hat dot. Okay, er hat dot I can take from here and put it as theta dot times e theta hat. Okay, which is what I will do right away. Theta dot times e theta hat. Okay, maybe erase these to keep the clutter. We don't need to simplify any further because we have it in terms as a component of in the radial direction, a component in the azimuthal direction. Okay, the component in the radial direction very clearly is just r dot, the change in the magnitude along the radial direction. Very straightforward, very similar to your x dot I hat or a y hat, y dot times j hat, right? But what is interesting is the second term in the theta direction. You don't have just a theta dot because that's a radian per second. We want it in units of meter per second because we're talking of actual velocities, translational velocities there of that particle, and therefore it is r times theta. The dot is over the theta alone, right? So that's the expression for your velocity. So even though you had only 1 term for the position, you have now 2 terms for the velocity. Coming to acceleration, things get even more messy, right? So let's try to get to the acceleration now. The acceleration is the double dot of this. So I have to once again use the product rule. In the first term, it's a little simple because there's just 2 terms multiplying each other. Here there are 3, so you have to take one at a time, the time derivatives of each one of them, which is what we will do next. Okay, so r double dot is what we want. Let's take the first term there. That's going to be, let me write it here separately. So first term I take r double dot, keep er hat as it is. Then I have to keep r dot as it is and multiply it by er hat dot, right? So er hat dot, I already have an expression from there, okay? So I will just take that into account. So er hat dot is theta dot times e theta, okay? It's very clear. So this first term is what we are taking the time derivative of. So we use the product rule. First we take the derivative of r dot, it becomes r double dot, and keep the second term er hat as it is. Now we keep the first as it is, that is r dot, and take er hat dot, which we have substituted from here, namely theta dot e theta hat, okay? So that takes care of the first term. Now let's go to the second term that we have here. Now we will see that we have to do it 3 times. One at a time we'll take the derivative, keep the rest the same. So the first contribution will be r dot theta dot e theta hat, right? So that is r dot theta dot e theta hat. Immediately you will see that this is identical to the second term that we had already got. So we can combine those two as twice. Okay, we'll do that later, but just for that sake I've written it one below the other. So now we are already done with the first term of this triple product that we have here. R dot is taken care of. Now we keep r the same, take theta double dot, and then e theta, right? Yeah. Now that is done. Now the only thing that is left is the last term, that is r theta dot times e theta hat dot. E theta hat dot we can substitute from here. So let's go about this over here. So since it's going to be a minus sign, I will put a minus sign already over here. I'll keep r and theta dot as they are. R and theta dot are as they are, and then e theta hat I have to take a dot, which I already have over here with respect to I, and therefore it is the negative sign I have already put. So all I have to put is a theta dot times er hat. So that theta dot becomes squared er hat. Okay. So now we have the complete expression for the acceleration over here. Now we can combine the terms which are part of er hat separately and those which are part of e theta hat separately. When we do that, we get the acceleration in the inertial frame in polar coordinates is given by the er hat term is r double dot minus r theta dot squared. That's along the radial direction. Similarly, along the azimuthal direction, we have two terms identical, so I'll put them as twice r dot theta dot, or maybe I'll put this term first. I'll put this term first, so which is kind of more obvious term. And then bring these two together, twice r dot theta dot. I can take the e theta out. Sorry. Okay. I hope this is clear. Now, if you look at it from what we are familiar with in the Cartesian coordinate system, if we write the acceleration, remember that we just write it as x double dot I hat plus y double dot j hat. Remember, we are talking of 2D planar motion, so there's no third term. Okay, so very similar to that, I like having an x double dot and a y double dot. We also have the first term here, r double dot along er and theta double dot along e theta. And just to take care of the fact that theta is not a length dimension, we have an r multiplying that. Okay, so r theta double dot is that contribution. So those look very similar and familiar. What is different and what is the new intuitive thing that you have to think about a little more is the second term in both of these expressions. Okay, along the radial direction we have now a new component which is along the negative ER direction. Remember that ER is always outward from the O, ER hat is always positive, right? There's no negative, it means going towards the center, which is what this is. It's saying that negative ER hat means it's not going away from the center, but it is going towards the center, okay? Which is what we call as, and it's a very common term in the Indian parlance also, is about seeking and going inwards, which is all meditation is all about. You're not going outwards externally, but internally towards you to find out, first of all, what is the subject before you find the object. So that's your, along with the negative sign, that particular term is what we call as centripetal. And that word itself, centri means to the center, and petal means seeking. So essentially centripetal, even from its etymology, you will see that it's nothing but seeking the center. Okay. On the other hand, here we have a term here as well, 2r dot theta dot, which is named not in an etymological sense, but by one of the persons in the West who first discovered it over there, which is again a French mathematician like Frenet and Serre. This is Coriolis. You might be familiar with the term Coriolis effect or Coriolis force or Coriolis acceleration, which is what this is. This is also centripetal acceleration. Right, so it's named after that French mathematician about, let's say, in the 1790s or so, so about 250 years, a little less than that, when this particular method or the term was given a name. People were using it before that, even in the West, but without giving a specific name to it. Now, if you look at it, one is compared to what we know intuitively, we have an additional term in both. But both of them have certain commonalities. One is in velocities, of course, we expect first derivatives. In acceleration, we typically expect second derivative terms like this, x double dot, y double dot, r double dot, theta double dot. But you see, you do not have any double dots in these two terms. You have only single dots. That is, you have only a theta dot there, and you have a r dot and a theta dot over here. But unlike the other terms which are all linear, see, x double dot is appearing as power 1, y double dot is appearing as power 1, and it's not multiplying any other independent variable. Similarly, r double dot is appearing power 1. Theta double dot is appearing 1, but it is multiplying by r. Okay. Now, both r and theta are independent variables. Okay. So there it is appearing as a quadratic kind of a behavior. On the other hand, if you look at the derivatives, those derivatives are first derivatives, but they are appearing as a product, theta dot times theta dot times r dot. Okay, so it is this which is again unique about these two new things that we have discovered just by going to a different coordinate system. As I have been telling right from the beginning, whether it's the frame of reference, coordinate system, or unit vectors, these are all tools for us to get to the truth. Now, you can use whichever is convenient to you. You should end up with the final result the same, whether it's the acceleration or the forces or whatever you want to determine eventually in terms of its magnitude, in terms of its direction with respect to any other frame of reference which you keep common. After you're done with your methodology, I'm done with my methodology, we compare according to that common frame, we should have got the same answer irrespective of which method we have used. So it's a kind of something that is coming because of the fact that we are using a coordinate system in which we are not using all length measures, but we are using an angular measure. Okay, and once you bring in the spherical coordinate system phi as well, which is the polar angle in the spherical coordinate system, these things become even more messy. But just that, now that we have understood what is the physics or the math behind that, we can more clearly start seeing things. Now let's look at some practical examples so far as mathematics is concerned, but nothing for engineers is good enough with pure math alone, right? We use math as a tool in order to understand the science or the physics. So in this particular case, we are trying to understand what is the actual physics going on there. Are there certain practical examples where I can recognize this? Now, can you think of some practical examples of centripetal acceleration, or even more so, let's take a step forward and say centripetal force? Examples in reality where centripetal force occurs. Centripetal we have already defined as something which is seeking the center, which means that it's along the negative ER direction. And if you're looking at it from quantity that you are familiar with, theta dot as angular velocity omega, so you're looking at omega squared r, okay, term that you're very familiar with, which is taking you towards the center rather than away from the center. Okay, so anything that you can think of as practical examples, SVT? Good, yeah, okay. So what is actually happening over there? Can you tell the terms what they mean over there?
So I guess like
No, in terms of r and theta dot, what are we talking about there? Right. It's a good example. Yeah. It's crying for attention.
I think R would denote like the length of like a blade,
Yeah.
and theta would denote I guess the angle at which it's I guess it's a little confusing to make the relation between that. It feels a little abstract, but like I'm trying to think of when a force is being applied
Mhm.
in a certain direction, the theta would be the angle between. I'm not really sure.
Okay. Anybody else can help out? Yeah, Daniel.
About that example or a different one?
Yeah, same example. Then we can go to your example.
Okay, I think so. The first term is r double dot, and the blade length is not changing at all, so that value would be 0. Then the second term, we have the radius of the fan blades, which we know,
Mhm.
and then theta dot is like the angular rotational speed of the fan squared.
Mhm.
So the faster that the fan would be spinning, the more the blades would be accelerating inwards towards the center, which makes sense because if you spin the fan really fast, you have to hold onto the blades harder, or they might go flying off.
Okay.
At least that's what I thought about.
Okay. Before we go to your example, let's talk about a little more about Vitti's example. Remember that whatever we have done so far, we are treating this as a particle, not a body. Okay. Whereas this blade is a body. Okay. But the body is made out of particles. Okay. And you said that, for example, that your r double dot is not having a contribution there if we treat it as the blade as a rigid body. Okay. But in reality, it's made out of a metal which has a certain Young's modulus, which is finite, and therefore there is a slight extension. Okay. And coming to theta, you start from any particular location of the fan blade, which you can call as 0. It's your reference. From there, whatever angle it turns, I'm doing it very slowly, it's doing faster than that, but essentially that is the theta, that angle that you go. And how fast you go measures your theta dot. What you in more common engineering parlance call as the RPM, the number of revolutions per minute, which of course you can convert to radians per second by just having 2 pi radians for 1 revolution and 60 seconds for 1 minute. So you multiply by that conversion factor, you will get in the radians per second that we would want to have that. Now let's break that further. Okay. Now as I said, this is not for the entire blade, but for every particle on that blade. The blade is made out of a large number of particles. Okay. Now, if we take any particular particle along the length of the blade, it need not be at the tip of the blade, which means that it's not the radius of the fan itself, but how far is one particular particle that we are tracking, and then we want to see how far it is from the center of the hub of the fan. Now, that distance r is what we are talking about as over here, and that, as you rightly pointed out, in a rigid body case, that will r dot is 0 and r double dot is also 0, but in reality there will be a very, very small motion. Again, depends on the fan speed. If I turn that regulator 1, 2, 3, 4, 5, the RPM keeps increasing, and as the RPM keeps increasing, the amount by which it gets pulled out is much larger, and that's what happens. Now, the centrifugal force that centripetal force that we are talking about is the way the blade is, if you look at one of the fans which is stopped, you see that the blade is attached to the hub. So it's essentially that attachment that we are talking about. So it's not able to get off that, right? So that attachment is what holds it back. So that is what brings you back to the center, brings the blade back to the center. So that's what is the petal there, seeking the center. Okay, seeking, and this is centri is essentially seeking the center. So centripetal is making sure that the blade doesn't go off. So suppose some of those bolts have worn out or let's say damaged, and when you start increasing the speed and run it for a reasonable amount of time, the blade can just come off because of the absence of the centripetal force. What bolts were holding it, now they're not able to hold it and it goes off. So that's essentially your centripetal. Now let's come to your example.
The other example I was going to say is just like the classic physics demonstration where someone swings a bucket full of water around, and the reason I guess why the water stays in the bucket is because the bucket has to accelerate inwards, so the water can't fall out.
Absolutely, yeah, very, very good example there. Now, what is the physics behind that? What is actually providing the centripetal force? In this case, as the example that I gave, that Viti gave, we said that the bolts, whatever the bolts, the stress that is created within them is trying to bring them back in. What is trying to bring that back in?
In that case, it would probably be like a rope of some kind.
So what is there in the rope?
Tension.
Exactly. So the tension in the rope is what is causing that so-called centripetal force. Very good example. Anybody else? Any examples you can think of from real life?
Earth rotating in
Very good. Yeah. So very good. So Earth rotating around the sun, right? Revolving around the sun. Yeah. So when the Earth revolves around the sun, what happens? Why is it not just escaping? Why is it continuing to go around the sun?
pull by the sun.
Exactly. So the gravitational pull by the sun is towards the center. So that's exactly what you're talking about, centripetal, seeking the center, where the center there happens to be the sun. Okay. So for all planetary motion, that's essentially what is happening, which is around the sun, or even the satellites like the moon around the earth. Those revolutions are essentially created by gravity. So now we talked about the bolt, we talked about tension in the rope, now we talked about gravity. Three sources of centripetal force or centripetal acceleration. Anything else? Yes.
There's a roller coaster that does the loop
Very good. Yeah.
as well, because you feel like you're falling out of your seats.
Yeah,
or
yeah.
being pushed into your seat.
Yeah. So being pushed into the seat is essentially the opposite of this centrifugal force, because you're going away from it, right? Away from the center. You're not seeking the center, but you're moving away from the center, because if you're rotating like this, you're essentially being pushed out, right? Which is why you feel heavy on your seat. You're trying to be pushed out. Okay, that is the absence of centripetal force. Okay, so centrifugal by itself does not have an existence. Centrifugal, even though it's very more popular word compared to centripetal, people talk about the centrifuge, people talk about various centrifugal forces, etc. But centrifugal, remember, is the absence of the centripetal force. It's like the difference between darkness and light. Okay, darkness doesn't have an existence by itself. If I switch off the lights, it's night, let's say, it will be dark. Okay, it's just the absence of light which is darkness. Okay, something similar to that. But of course, it's all a question of observer perspective. Everything in science is subjective, depends on the observer, which is why we give so much importance to the frame of reference, right? So from that point of view, in a particular kind of framework, darkness might be the main thing, and I might think of light as the absence of darkness. Okay, I can put it the other way around. Same way, I can think of the centrifugal as the real thing, and then think of centripetal as the absence of the centrifugal. But for most engineering practical purposes, the way we frame our, way we bring about our frames of reference, it is the centripetal which is the true thing, and it's the absence of centripetal which causes the centrifugal effects like what you mentioned, Gracie. Yeah. Anybody else? In terms of the sources, we're looking at the bolt, we look at tension, we looked at gravity, anything else which can cause that.
Atom and electrons.
Very good. Yeah. Very good. Very good. Yeah. So you're going from a very large length scale to a very small length scale. So it's the beauty of the way physics and science works. So many things are kind of similar at very small length scales as they are with the large length scales. So here the electrons going around the nucleus, which has the protons and the neutrons. And so essentially, what is the force there?
The energy, the nucleus has the positive energy, whereas the electrons have the negative energy. The attraction between them causes them to string along the same orbital,
Yeah.
instead of flying.
So it's essentially the electrical field that you're talking about, the electrical.
I'm not very sure.
Yeah,
I may
yeah.
be wrong in
Okay.
terms of that.
Right. It's the electromotive force that you have between the proton and the set of protons and the electron, which makes sure that the electron continues on that. Of course, you can supply enough energy for the electron to escape, in which case the atom becomes the ion, etc. Right? So you have to have a minimum amount of threshold energy in order to do that. Okay. Anything else? Let's come back maybe to aerospace engineering. We are all aerospace engineers, and AE2220 is what we are looking at. Any example in an aircraft in its entire phase of flight where you think this is coming into picture?
Escape velocity.
Yeah, very good. Yeah. So what can you explain that?
The amount of escape velocity it has to have in order to come out of the centrifugal force or centripetal, centripetal force.
Yeah.
It has to get into that orbit and then punch out.
Exactly.
That.
Exactly.
Otherwise, it wouldn't ever get out of the orbit, and it will still be there. And
Right.
in fact, if you really put it there, it has got different levels of orbital levels, like space station, higher orbitals and higher planets.
Yeah.
So as we go up and above, the energy levels become lesser and lesser and lesser.
Right.
Therefore, the pull becomes.
Yeah. So orbital transfers is what you're talking about, from one kind of an orbit to another kind of an orbit. Essentially, it's the same problem that we were talking about earlier, the planetary motion around the sun.
Yes.
The source of that is still the gravity. But just that the acceleration is so large that it becomes no longer possible for that body which is exerting the gravitation to hold on to it, and therefore it escapes. Okay, that's your escape velocity that you're talking about, which is same as Gracie's example of that whatever, in a ride that you're going through, or a merry-go-round, whatever, the giant wheel. Essentially, it's trying to pull apart, right? So beyond, if it is rotating at beyond the design speed, yes, you could be just thrown out, right? So that's essentially what's happening over there. Yeah. Another example from aerospace.
So, if you try like taking a turn and or doing it during flight, if you're doing a maneuver where you turn inwards, obviously there's that centrifugal force we talked about where it's a lack of centripetal force, but you feel the air resistance pushing you inwards. Right?
Yeah.
So would that count as centrifugal forces?
Absolutely, yeah. So essentially anything which is trying to push you towards the center or pull you towards the center is the centripetal. And when it is absent or is insufficient, like the example that he pointed out with the escape velocity, essentially it seems like a centrifugal, but it's only the absence or inadequacy of the centripetal. Okay. So another example, you guys presented the Falcon today, okay? And one of you, the second example you talked about is the Falcon going straight up and then taking a 45-degree turn, right? So as we discussed there, it cannot do that abruptly. So in other words, it goes on a vertical path, and then before it gets onto that 45-degree path, it has to take a curve. Yes.
Can they not try?
Can they what?
Can they not try to do it?
Not try to do it?
Yeah, can they try to do it like
Sharp.
in the sense, yeah.
Uh,
If, for example, if they are out of the gravity sphere,
Mhm.
right? Correct?
Yeah.
Then they can pretty much do whatever they want, right? Abruptly or non-abruptly, even if they are moving at massive speeds.
yeah. So
Like for example, how satellites today, once they are in orbit, they can be rolling over any which ways how they want to, right? They need to be
yeah, it
careful
depends
that-
on where they are, because they
Yeah,
can be
they
in
cannot
other
do small
some other
things
gravitational
there.
field as well.
They cannot do small changes there. They need to be drastic changes so that it stays like that.
Yeah, so whenever you do a drastic change, what happens is the stress levels become very large. So from a material point of view and the structural integrity point of view, that will be affected. Theoretically speaking, what you're saying is right, just that it's not only the gravitational field which exists, okay? The forces which are acting on it because of the thrust are essentially being resisted by the material that the rocket is made out of.
I just wanted to say, I think it would be possible if the
Would be
rocket-
possible?
It would be
Uh-huh.
possible to do like a hairpin, like instantaneous turn,
Mhm.
if it was designed like one of the military like fighter jets that have
Yeah.
high instability.
Right,
Because if
right.
you look at videos of those, they'll go like this and then just take a 90
Exactly,
degree
yeah,
upward,
yeah,
just
yeah,
at a
yeah.
hairpin, and they'll be going at constant velocity this way and continue that upward.
Right, right.
But that would require like probably the rocket would have to be manned first of all, and you
Uh-huh.
need a high level of control over the rocket because it's highly unstable in order to be able to make the turn in the first
Mhm.
place.
Yeah. So whatever you're saying is essentially the systems that we're talking about. Whatever he talked about or you talked about essentially is in terms of the relative orders of magnitude. So if you're looking at such a high speed, even though it might be a curve, it appears as if it is sharp for you. Okay. It can never be absolutely sharp.
Right.
In other words, it's a question of that radius of curvature. That radius of curvature can get very small. Okay, then it seems almost like a sharp turn that essentially is being taken. But nonetheless, once you do that, you end up with stress concentrations, and it could be disastrous for the vehicle as a whole. So it's a question of how strong and stiff you have built the vehicle. One, the other is in terms of how small can you go to the radius of curvature. It will never be zero, but it can be very small, and at the speeds at which this turn is occurring, it seems almost like it's a sharp turn. Okay. So another very common example is in your aircraft which is taking off. Okay. So when an aircraft is on the ground, it is on the runway, it is after taxiing, it's essentially ready to take off. So it's going on the runway with its engines on. At some point, it essentially changes its pitch angle, right? So that change is again not happening sharply. It's happening over a small period, but because of the speeds, takeoff speeds being fairly large, you see almost it's going like this, but essentially that's a curved path that it is taking as well. So what causes the centripetal force there?
That's right.
No? You see what I'm saying, right? So
Inertial mass.
this is the aircraft which is going on the ground, okay? And at some point it is taking off like this, okay? So the curved path that I'm talking about is this path that it is curving over here, right? So the center of that curve is over here, right? So in other words, there is a force which is pulling it that way, which is causing it to go up. What is that force?
Inertia.
Yeah, lift. Lift by definition is perpendicular to the velocity. Drag is always parallel to the velocity, of course in the opposite direction of the aircraft's velocity, but same direction as the air's velocity. So now when takeoff is happening, you see that initially the weight was so large that it is still holding to the ground. The lift was not large enough to match it. As you increase the speed on the ground, you reach a certain speed where the half rho v squared SCL or and CL almost close to CL max, because you're deploying the flaps over there in takeoff, and therefore it is essentially creating a large enough lift to make this path curved. And so you see that curved path that is there, your lift is perpendicular to the velocity direction, therefore it's going towards the center of that curve. And therefore that is the centripetal force that you're having over there. Another example?
If centripetal force wouldn't have been there, I think the funniest question is the aircraft need not have to take off or do all that. You just jump and then you make sure that it stands still there. Earth will automatically rotate and then you fall down.
Right. Yeah. Any other example?
No, I think that
On appeals to you, being a pilot. Yeah. Anything else? So we talked about flying vehicles, both rockets and the aircraft. What about ground vehicles? You're taking a turn.
Racing vehicles taking
Yep.
a shot.
So Nafi's got it right. The source of that is friction. So if there wasn't friction, it would just, whichever direction it's turning, it opposite direction away from the center, it will be thrown off, right? But the fact that there is friction is what makes it stay on its circular path. Yeah.
if you see in that context, if there is no friction, right? Like a car would keep on skidding, then that wouldn't be the thing that we are looking at. It would not technically be.
No, see, once this particular thing is absent, this is the source which is kind of making it continue on that path. If that source is removed, okay, to give you a very simple example, because friction is a little tougher topic in tribology. Suppose I have a rope, let's say, something like this, okay, and I try to tie something, a mass at the end, and I go around, right? So now because of the tension, it is getting pulled, okay. Now suppose I do the same thing. Now I'm turning like this. Now while I'm turning, I cut off the rope. Where do you think the bob will go?
Tangential direction, right?
Yeah, why?
Because the acceleration is always in that direction. Every angle that we turn is a acceleration which is turning towards centripetal force. So therefore it has to go to...
Right. So essentially it's Newton's first law. Whatever body is moving in a particular velocity continues to move in that velocity unless and until acted upon by an external force. That external force, whatever was acting, is the tension in that rope. So that once I cut the rope, the tension is vanished, centripetal force is vanished. So no longer it can continue on a circular path. It goes off on a straight path which is tangential to the direction wherever it was cut off. Yeah.
You
Yeah.
have bank in the
Yeah.
road.
Yeah.
It's typically to ensure that he gets into the curvature while he takes it, despite he goes to that.
That's right. So essentially you want to make a particular component of the weight
Yes.
to support your whole thing, which is essentially the banking angle. You see an exaggerated version of that you will soon see in Olympic Games in Paris, where you will see that cycling especially, you'll see the paths are essentially pretty much fairly steep slopes, right?
Circus chap
Yeah.
who goes around.
True. Yeah. So many examples like that. So right from our day-to-day examples as well as aerospace that we have seen, and natural bodies like planets, satellites, etc. that we have seen as far as centripetal is concerned. What about Coriolis? See, also let me say step back and say, see, for this to happen, r should not be 0. In other words, this cannot happen at the center of the rotation. Okay, it cannot happen if theta dot is 0, which means that there has to be a non-zero angular velocity for this to happen. Okay, and it's always in the radial direction and a negative radial direction more precisely. Now we come to this new guy that we have found here, Coriolis acceleration or Coriolis force or Coriolis effect, whatever you want to call it. Now if you look at it, it's having once again first derivatives only like that. That is the commonality. But that it's also having a theta dot. If theta dot is 0, it will not be there. But in addition to theta dot, we require an r dot. So in other words, there is a radial velocity. There is also an angular velocity. Only in the presence of both of those, this will occur, and this will be in the tangential direction. Okay. Unlike this, which is the radial direction, this is in the tangential direction. So can you think of any practical examples? Yeah, Gracie.
So it's like the winds and the spinning of the globe that causes them to
Very good, beautiful. Yeah, that's a very important example, and in fact, a big headache for many of the weather specialists studying atmospheric science, because so very difficult to predict that, right? So the wind currents, the movement of the clouds, even the ocean currents for that matter, all of these are governed by that, and like the season that we are going to have here, the monsoons, all of that, when it onsets, how it moves, etc. Many of these are governed to a large extent by the Coriolis forces that are involved over there. Yeah. Any other examples?
I'm not sure how this would totally change the acceleration, but I guess if you had an airliner that was like it was ascending, increasing in altitude, and it had an angular velocity because it was moving around the Earth, then that would change its angular acceleration in the Earth reference frame.
Okay. So see, in this case, you need both of these, right? So which means that, for example, if it's performing a maneuver, maybe a group captain might be able to explain it better with another example. But essentially, suppose instead of going through a circular path, you're trying to change the radius of that path, okay? Either increase or decrease. Then what you're having is, you're having a certain radial direction, you can also having a certain angular direction. That will cause you this particular Coriolis acceleration. Any examples you'd like to share? Yeah.
I'm just thinking of gyroscopes.
Yeah. Sure,
Because
sure.
In this case, suppose there is a rotating
We have
wheel,
one over here.
while rotating
Yeah.
wheel,
Uh-huh.
try to change the direction, it resists that
Correct.
particular direction.
Right, right.
So isn't that
Sure, but it also requires something to be moving on the
Moving on.
radial
correct?
thing. So because you need the r dot as well.
Yes.
So that's what is used for stabilizing.
Gyro stabilization.
Yeah, absolutely, absolutely. Yeah, true. That Coriolis plays a role there as well. Yeah. I don't know if you have played this game. We used to, when we were very little children, going on merry-go-rounds. And when we were going on merry-go-rounds, two of us sitting opposite each other and passing a ball to each other, okay, while the merry-go-round is rotating. Now, I think I'm really good at it and try to throw straight to him. Yeah. By that time, he's gone over there already and it goes to Nanjapa instead, right? So that's exactly what happens. So I have to make a correction for that. And instead of, if I want to throw it to him, I would rather throw it to Nafis, and then it goes to Chinababu, right? So that's one effect. So because what is happening over there, the ball is coming, now this is the center of the merry-go-round, we are going round. So there is a radial direction, which is the radial velocity r dot, which is coming from the ball, right? And the merry-go-round is going round, which is having an angular velocity theta dot, whatever its RPM is. Based on that, the theta dot, both being non-zero, will cause a certain tangential velocity, which is what is the E theta hat that you see over there. And therefore, it is going in a slightly away from wherever it is supposed to go to, okay? So even though I'm giving only a radial component, I'm thinking, but it is getting a tangential component because of the non-zero value of this particular term, okay? So just remember this fact that pretty much everything that we talked about, friction, tension, gravity, lift, all these things, examples of centripetal acceleration, whereas centrifugal is only the absence of those. So the examples that I gave, we cutting off that thread, which means the torsion is gone, or suddenly, let's say, when the vehicle is taking a turn, you put oil on the road, and essentially the friction is gone, so it skids, right? So things like that, where essentially you're taking out that whatever, or the escape velocity that you talked about, where you're going at such a high speed now that the gravity is not strong enough, forceful enough to hold it. So all these things are either reducing or bringing to zero the centripetal force. The source of the centripetal force is taken away, let's say, then you end up seeing or imagining a centrifugal force. It's not really there. It's like darkness, which is the absence of light. On the other hand, the Coriolis acceleration is something, again, just like the centripetal, makes a huge difference in a lot of different motions, especially a lot of aircraft maneuvers, etc. utilize this. Right now, remember that we are still talking about particles, and aircraft is not a particle, it's a rigid body. It will have its orientation, rotations, etc. So even just because of angular motion, without even talking of the rotation of the body, there are so many complications. Once we bring in the rigid body and its rotations like pitch, yaw, roll, etc., then you will see that you need a whole different paradigm over there. But all of these are building blocks towards that, because these particles that we are talking about, remember, are the ones which make up the rigid body. Okay, just that the distance between two particles remains the same, a constant, which is what we are saying when it's not flexible. Okay, it's rigid. Therefore, by employing those constraints in a minimum number of points, which we will see what the constraints are, etc., then we will see that these same things that we have derived over here, even though they are meant for particles, can help us to derive the rigid body equations of motion, which we will do in a later class, right? Now, coming back to the two guys whom I introduced you to in the morning, Frenet and Serre, it's not just the kappa and the tau that they introduced, but they also introduced the correlation between them, okay, which is called as the Frenet-Serre formulae, which I will list out, and then we will briefly discuss that. It's easiest seen in a matrix form. So remember that already we have seen this particular coordinate system. Apart from Cartesian coordinate system, I hat, j hat, k hat, we looked at the polar coordinate system, er hat, e theta hat, e z or k hat, and then the spherical coordinate system where we had er hat, e theta hat, e phi hat, without going into the equations. But I also very briefly introduced to you and talked about it every now and then, is that so-called natural coordinate system. Okay, so the natural or intrinsic coordinate system. So this is for any space curve that you might have, and of course the special case of that is a planar curve, and the even special case of that is a rectilinear straight line, right? Now when you have a space curve like that, there is something called the tangent to that, and if you have a unit vector at any particular location s of t, then you will call that as et hat. Okay, and then there is something which is normal to that towards the center of that curvature, which we will call as en hat. Okay, and if it's a planar curve, then just out of that plane, which is et cross en, I would get what is known as a binormal, which we will denote by BEB, B standing for binormal. Okay, so you have what is tangential, we have a normal, and we have a binormal. Okay, now what the Frenet-Serre formula do is, and why do we call it intrinsic? It's because it's associated with that curve. Whatever is the path of that particular particle that we are tracking, particle P, starting from some s of t, which is s of 0, to reach at the particular location s of t. So that curve that the particle is tracing, it is intrinsic to that. Okay, and each time it traces a new path, you have a new set of unit vectors associated with it, with that new path that it is tracing. So it becomes much more convenient to look at certain physical aspects of it, which is why this is so very important and very commonly used even in aerospace engineering. So tangential, normal, and binormal. How do you get to it? The tangential is just defined as the time derivative of the position vector. Okay, so your et is defined as with respect to any inertial frame, you have your position vector of that particle P with respect to T, okay? Or in our short notation, we can just call it P dot. Okay. On the other hand, your normal En is defined as your Et hat dot in the same inertial frame of reference. But this unfortunately doesn't have a magnitude 1 all the time. So you have to divide it by its own magnitude. These are all fairly easy things to derive, but it's all part of geometry and I do not want to take too much of the time in the class trying to derive that. So those of you who are interested, you can just go into looking at the derivations of these. But this is a definition nonetheless, it's not a derivation. So Et hat is defined as the time derivative of the position vector. So that's already a unit vector, you don't need to divide by anything. Next, you take whatever you got there, which is the tangential vector. You now get the normal vector by taking the next time derivative of that and dividing it by its magnitude, make it a unit vector. Okay. Finally, you have the binormal vector. The binormal vector is very easy to define now that you have two of them because you have a dextral triad. So you have just Et hat crossed with En hat. So these are the three formula we have for the tangential, the normal, and the binormal. Okay? Yeah.
Why is the time derivative of the position vector necessarily a unit vector?
Yeah, it's something that you can actually prove.
Okay.
It's purely a geometric thing. Just try to take a look. If you still find it difficult, get back to me and we will do it in class. Okay. So let me give you a very, very simple example. The simplest motion that we have looked at is, let's say, the rectilinear motion, right? In which case I can bring the origin here. I can put the position vector over here. So the position, this is the position vector, right? Yeah. So this is the position vector that you have. Now, if you want to take the time derivative of that with respect to this inertial frame, whatever is fixed over here, this is I. So I want to take the time derivative of that. You see that it's just nothing but x times I. That is what the position vector is, and therefore it just becomes oh, I'm sorry. Glad you pointed out. None of these are dots. I'm so glad that you would have messed it up. Yeah. So these are primes. Okay. So derivatives with respect to s. Thanks so much for bringing that to my attention. Okay. So these are all derivatives with respect to s, which is the prime. Remember we were talking about s of t. So this is the path. It's gone to s of t somewhere. So you're right that p dot will not be necessarily unity. P prime will be unity. Yeah. Okay. Yeah. Yeah. Okay. Now, yeah. So let me probably also make in this, which is s along I in this particular simple example, and therefore you are ending up with that, which is therefore in this case I itself becomes your tangential unit vector. Yeah. So coming back to the Frenet-Serre formula, it's essentially giving these three quantities: Et hat, En hat, and Eb hat. The tangential, normal, and the binormal that we just introduced, we want to get its time derivative. Derivative with respect to s, the arc length. Okay. So in other words, you have Et hat prime, En hat prime, and EB hat prime. Okay, so in other words, how are these unit vectors going to change with change in S, okay, on any arbitrary curve like this? Okay, of course valid for circle or straight line as well. Okay, now remember that they introduced the two quantities, curvature kappa, and they introduced the torsion tau as a function of S. Okay, now this matrix is a function of those, and it's a very, very simple and easy to remember function because it's a skew symmetric matrix, which means that the principal diagonal terms will all be zeros. Next, it makes it even simpler. Even the non-principal diagonal is also 0. And what is left is just those 4 guys, and since it's skew symmetric, only 2 of them are independent, and those 2 are nothing but, as you would guess, the 2 quantities which Frenet and Serre introduced, I talked about in the morning, the curvature and the torsion. So this is your curvature, a function of S, and the torsion, which is also a function of S, and since it's skew symmetric or anti-symmetric, you would have the negative of tau over here and the negative of kappa over here. While this is what you would see in most books, there are a few books, I should warn you, if you look at, where you would take minus tau here and a plus tau here, just that the sign convention they use for tau is different. Okay, but this is what is there in most literature, and this is consistent with what Frenet and Serre initially introduced, so we will stick to this. Yes?
Is this like a matrix form of a system of differential equations? The
Yes,
form looks
yes.
very similar.
Yeah, it is because these are all first derivatives,
Right.
and these are the same functions. So essentially you are relating the first derivative of the function to that through coefficient, which is also a function of the independent variable, because the derivative is with respect to S, and all of these are functions only of S. It's an ordinary derivative. So first order ordinary differential equations. So if you expand and write this out, the very first equation will be Et prime is equal to kappa times En prime. Okay. So, but it's a coupled set of equations. There are 3 unknowns, 3 dependent variables, Et hat, En hat, and Eb hat. All of them are appearing only as first derivatives, and it's a linear equation as well, because they're all appearing as power 1 and not as products of each other, same way over here, and which is fairly easy to solve once you know the functions kappa of S and tau of S, which define the particular function. Okay, let's take the simple examples that we are already familiar with. What is the in the case, the simplest thing that we started off is the rectilinear motion, the straight line, right? So when you are having a straight line motion like this, the rectilinear motion, what is the value of those 2 functions that Frenet and Serre introduced? What is the value of kappa for this curve?
0.
Yeah, identically 0. Right? What about tau? Yeah, because any planar curve should have that equal to 0. Okay, so suppose I put zeros there, this becomes a null matrix. So the right hand side entirely becomes 0. What does it mean? All the primes are zeros, which means those quantities are constants. You end up with your Cartesian coordinate system, I, J, K, remember? Those are the ideal ones for this kind of a system over here. I along the path, J and K perpendicular to the path, and all 3 are constant even as the particle moves and S changes with time. You will have I, J, K constant, which is what is meant by these 3 guys being zeros, the derivatives being 0, and therefore the unit vector itself being a constant, and that constant of magnitude of course is 1 because it's a unit vector. Yes, Andrew?
So I have 3 questions. So
Yeah.
first, is this squiggly bracket notation just to notate that there's like a curved space, or what is that exactly?
Which notation?
Like around the derivatives, it's like squiggly.
This one? This one?
Yes.
Yeah, it's just a column matrix. Okay, the braces.
Okay.
I'm just putting braces around that. Okay, it's like a 3 by 1 matrix here, right? 3 rows, 1 column. You have a 3 by 3 matrix over here, and you have a 3 by 1 matrix over here, right? So end up with a 3 by 1 on the left hand side.
And then I was also wondering,
Yeah.